The universe is composed of tiny particles called atoms. All matter, everything in the universe, is made up of these building blocks. The atom is made up of three fundamental particles: protons, neutrons, and electrons. The central part of the atom, the nucleus, consists of protons, particles with positive charge, and neutrons, particles with no charge. Orbiting around the nucleus are negatively charged particles, electrons. The earliest observations about matter can be traced back to Greek thinkers. Leucippus thought matter could be divided into smaller and smaller pieces by being cut up, but only so far. Eventually you would come to a piece you couldn't divide. He called this piece atom. In fact, atom means not cuttable. Another Greek thinker, Democritus, extended Leucippus's theory. He contended that all matter is made up of small particles which could not be further divided. An English chemist, John Dalton, was the first to propose an atomic theory. He suggested that an atom is like an indestructible ball held together by some unknown force. Dalton also believed that everything is made up of atoms, and that the atoms in one thing are different from the atoms in another. But he also believed that many things are combinations of different atoms. This famous observation, offered around 1805, is known as Dalton's atomic theory. In 1897, experiments by another British scientist, J.J. Thomson, suggested the presence of smaller particles within the atom. Thomson proved that the atom has smaller parts called subatomic particles. We call them electrons today. And Ernest Rutherford, another Englishman, devised experiments in 1910 that strongly suggested there were positively charged particles in a nucleus. We now call these protons. Shortly thereafter, a Danish physicist, Niels Bohr, made an important discovery about electrons. He determined that the electron's orbit around the nucleus of the atom changes as energy is taken in or given off. Bohr's theory of atomic structure gave scientists a model showing different energy levels, or shells, where electrons are located. In Bohr's model, each orbital shell could contain only a certain number of electrons. That number, referred to as an atom's valence number, determines how certain atoms combine with other atoms to form compounds, and not with others. It explained also why certain elements are chemically stable. That is, they won't combine with any other atom because its outer orbital shell is filled. Besides protons, Rutherford in 1920 also suggested the presence of a neutral particle in the nucleus, which he called the neutron. In 1932, the English physicist James Chadwick proved the existence of the neutron. As you can see, much of what we know about the atom was learned in recent times and continues to be refined today. To fully understand the role of the atom in energy production, it's important to know what its structure looks like. The nucleus is the center of the atom, and electrons revolve around it. Orbiting electrons, which have a negative charge, are attracted to the protons of the nucleus, which have a positive charge. This electrical attraction is what helps keep the electrons orbiting around the nucleus. This attraction of opposite electrical charges and repulsion of similar electrical charges is referred to as electrostatic force. An atom is electrically stable or neutral when it has the same number of electrons as protons. If an atom has more protons than electrons, it is said to be a positive ion. Conversely, if an atom has more electrons than protons, it is said to be a negative ion. But what about the nucleus? What keeps the repelling positive charges of the protons from breaking the nucleus apart? The answer is complex. Located in the nucleus are particles called neutrons. Although neutrons are neutral, that is, they do not have any electrical charge, they do add mass to the atom and help stabilize the nucleus. Neutrons by themselves, however, cannot hold the nucleus together. Besides gravitational attraction between nucleons, that's what we call particles in the nucleus, scientists, including Albert Einstein, theorized that there must be a nuclear force or energy that helps hold the nucleus together. Although it is not fully understood, scientists believe that the nuclear force, an attraction force, exists in the nucleus between any pair of nucleons: proton-proton, neutron-neutron, and proton-neutron. All of these forces combined form the nuclear glue, sometimes referred to as binding energy, that holds the nucleus together. As you will see later, when a uranium atom fissions, or splits in two, some of this binding energy is released as heat. However, don't think that all atoms are alike. There are 92 naturally occurring different types called elements. Elements are identified by their atomic number. An element's atomic number is determined by counting the protons in the nucleus. Since most atoms are electrically stable, that is, they have the same number of electrons as protons, the atomic number also tells how many electrons the atom contains. Beryllium, with an atomic number of 4, has 4 protons in its nucleus and 4 electrons orbiting the nucleus. Gold, atomic number 79, has 79 protons and 79 electrons. Gold is one of the heavier elements in nature. Adding the number of neutrons and the number of protons in an atom equals the atom's mass number. For example, helium has 2 protons and 2 neutrons. Helium's mass number is 4. As an atom's mass number increases, the atomic weight of the atom increases. As the number of particles in the nucleus increases, more nuclear force or binding energy is required to hold all the particles together. Most atoms also have different forms called isotopes. Let's take a closer look at the element hydrogen. Hydrogen has 3 forms: protium, deuterium, and tritium. All 3 have 1 proton in the nucleus, but deuterium also has a neutron in its nucleus, and tritium has 2 neutrons. Although all 3 forms have an atomic number of 1, each has a different mass number. Deuterium and tritium are isotopes of hydrogen. An isotope of an element has the same atomic number, that is, the same number of protons in its nucleus, but a different number of neutrons. Therefore, it has a different atomic mass number. As you'll see later, certain isotopes of some of the heaviest atoms, such as